Alright, so in this video I'm going to go over the molecular orbitals of period 2 homonuclear diatomic molecules. So period 2, that just means the second row of the periodic table, and homonuclear diatomic means you have two atoms of the same element bonded together. So the first element in the second row of the periodic table is lithium. So if we were to look at the molecular orbital diagram for Li2, it would look like this. You have your lithium atoms on the outside, and you have the atomic orbitals on the outside, and then you have the molecular orbitals for the Li2 molecule in the middle. So each lithium atom has one valence electron. So I'm going to go ahead and fill out the one valence electron for each lithium atom. Lithium actually has three electrons, but it only has one valence electron. So remember that when we talk about molecular orbitals, we're talking about the valence atomic orbitals. We're not really going over the core electrons. So each lithium atom has one valence electron, and when they combine, when the two 2s orbitals combine, they form the sigma 2s and the sigma 2s star molecular orbitals. The sigma 2s orbital is a bonding MO, and the sigma star 2s is an anti-bonding MO. This is very similar to the H2 molecule because the H2 molecule involves 1s atomic orbitals, and the Li2 molecule involves 2s atomic orbitals. So 1s and 2s atomic orbitals, they combine in a very similar way. So we have two electrons in this pool of molecular orbitals. So we fill them in lowest energy first. So that means this orbital will fill up, the sigma 2s, and the sigma star 2s will remain empty. So if we calculate the bond order of this thing, the bond order would be 1/2 times the number of electrons in the bonding MO, which is 2, minus the number of electrons in the anti-bonding MO, which is 0. 1/2 of 2 minus 0 equals 1. So that means that we have a positive bond order, which means that the diatomic lithium molecule should be stable. And it actually is. Normally lithium exists as just single lithium atoms. In lithium metal, that's how lithium exists. But in the gas phase, it exists as these Li2 molecules just because of molecular orbital theory. So the next element in the second row is beryllium. So let's look at the Be2 molecule. So remember, we're still talking about just s orbitals here because beryllium has two valence electrons, and those two valence electrons reside in the 2s orbital. So each beryllium atom has two valence electrons, and when those get added to the molecular orbitals, we end up filling them up as follows. We populate the sigma 2s orbital first, and then the two remaining electrons have to go in the sigma star 2s orbital. So if we were to calculate the bond order for this Be2 molecule, that would be 1/2 of 2 minus 2, which is equal to 0. So we would expect diatomic beryllium not to be stable, which is true. It does not exist in nature. So that does it for lithium and beryllium. And now let's move on to boron. Boron 2. So the interesting thing about boron is that, well, if you think about the ground state electron configuration of boron, that would be 1s2, 2s2, 2p1. So the valence shell of boron doesn't just have these s orbitals, it has p orbitals as well. So this is the valence shell, the 2s2, 2p1. That's the molecular orbitals that we're trying to figure out. So up until now, I haven't gone over how to do the molecular orbitals for p orbitals yet. So we obviously know that since the s orbital is completely filled in the valence shell, we know that there's going to be two valence electrons in the 2s orbital of each boron atom. So that means that we know that the sigma 2s orbital is going to be completely full, and so is the sigma star 2s molecular orbital. Those are going to be filled up because we start out with two completely full s orbitals in the valence shell. But what we don't know yet is how the p orbitals combine to form molecular orbitals. So we know that boron has one electron in a p orbital. Each of the boron atoms has one electron in its p orbitals. But the question on our minds is, how do these p orbitals combine to form molecular orbitals? Is it the same or is it different as when the s orbitals combine? And it's actually different. So to explain p orbitals a little bit, I'm going to show them pictorially like this. So recall that we have three p orbitals. We have px, py, and pz. The three p orbitals are mutually perpendicular, or they're orthogonal to one another. Each one is perpendicular to the other two. So what I'm going to do is I'm going to choose the x-axis to be the internuclear axis. So the x-axis, I'm going to choose that to be the axis that actually runs between the nuclei of the two atoms that are bonded together. So if I have a px orbital and I add to that another px orbital, if I linearly combine them like we've been doing for the s orbitals, these two p orbitals, these two px orbitals can combine in phase or out of phase, meaning they can constructively interfere or they could destructively interfere. So this is going to end up resulting in two different types of molecular orbitals. And the molecular orbital that comes from constructive interference looks sort of like this. And this is called the sigma 2p orbital. Sigma comes from the shape of the bond. It's sort of analogous to a sigma bond if you think back to valence bond theory, because there's a head-on interaction. This orbital is cylindrically symmetrical about the internuclear axis. So these are the two nuclei. And the other orbital that arises out of destructive interference, so instead of them constructively interfering, what if they were to destructively interfere like this? Then the molecular orbital would look like this. And these are the two nuclei, and the molecular orbital looks like this. This molecular orbital is called the sigma 2p star molecular orbital. So notice that I drew the sigma 2p orbital lower than the two px orbitals because, and there's a reason, it's actually lower in energy. In other words, this is a bonding MO. And the sigma 2p star molecular orbital, which has less electron density in this internuclear region, that's the antibonding molecular orbital. So now let's go over, now that we've gone over the sigma 2p and the sigma star 2p molecular orbitals, let's talk about the molecular orbitals that form when we start combining the py and the pz orbitals. So if we have a py orbital and we combine with that another py orbital, that's going to look something like this. And there's also two ways that the py orbital can interact. Those are in phase and out of phase. In other words, constructively or destructively interfering. And if we do this with a py orbital, it's going to look different than it did when we did the px orbital, because these py orbitals are overlapping sideways. They're not overlapping head-on. So the py orbital is going to look sort of like this, or excuse me, the molecular orbitals rather are going to look like this. Okay, so there's one. This is called the pi 2p molecular orbital, and I'll explain that in a little bit. And the other molecular orbital looks like this. And I didn't draw that too well, but oh well. And this molecular orbital is called the pi star 2p molecular orbital. We'll call it this pi star 2py molecular orbital. So The pi 2py molecular orbital is the bonding MO, and the pi star 2py is the anti-bonding orbital. The letter pi, what that's supposed to mean is just, again, it comes from the shape of the orbitals and the way that they're the side-on overlap, similar to a pi bond when you go back to valence bond theory. So that's the py orbital. And for the pz orbital does basically the same thing as what the py orbital does, only it's just shifted by 90 degrees. So if I add another pz orbital to this guy, then I'll get the same thing, the same exact thing, same energy, same everything as I did with the py orbitals, only it's just going to be perpendicular to the py orbitals. So I'm going to go ahead and I'm going to attempt to draw this. I'm not the best artist in the world, but here we go. So the bonding MO, if I add two z orbitals together, is going to look sort of like this. So imagine that the shaded region is behind the unshaded region. This is called the pi 2p ZMO. And the other molecular orbital, I'm kind of running out of space, so I'm going to draw it over here on the right. Looks sort of like this. And it has alternating shaded and non-shaded regions. And this is what we call the pi 2p Z star. Molecular orbital. So again, the py and pz orbitals form the exact same types of molecular orbitals, only they're just perpendicular to one another. And the px orbital, remember, because we defined the x-axis to be the internuclear axis, that's actually a head-on overlap, and it forms the sigma 2p and sigma 2p star orbitals that are entirely different from each of these pi 2p and pi 2p star molecular orbitals. So basically what we've learned in a nutshell is that when the three p orbitals combine, the three p orbitals result in a sigma 2p, a sigma 2p star molecular orbital, and also two pi 2p and then two pi 2p star molecular orbitals. And depending upon the elements that form the diatomic molecule, the energy ordering for all of these, because that's another question that comes up, is what is the energy ordering for this? Which orbitals are lower in energy and which orbitals are higher in energy? And really that depends on the individual elements themselves. So let's get into that a little bit. So first off, I'd like to point out that the energy ordering for B2, boron, diatomic boron, diatomic carbon, C2, and diatomic nitrogen, the energy ordering for these two is going to be entirely different than the energy ordering for oxygen, O2, F2, fluorine, and neon. So the energy ordering for these three is going to be different than the energy ordering for these three. And if it is boron, carbon, and nitrogen, then the energy ordering is going to look like this for the p orbitals. For the s orbitals, it's still going to be the same. You have the sigma 2s and the sigma 2s star molecular orbitals, and the sigma 2s orbital is lower in energy, obviously, than the sigma 2s star molecular orbitals. But the p orbitals, that's where it differs. So remember, if it's boron, carbon, and nitrogen, then that means the molecular orbitals are going to look like this. Note the energy difference of the molecular orbitals. We have the pi 2p molecular orbital is lower in energy, and there are two of them, remember, from the y and z axes. And then we have the sigma 2p orbital, and then after that we have the pi star 2p molecular orbital, and then we have the sigma star 2p molecular orbital. So these are actually going in increasing energy order. The pi 2p molecular orbital is the lowest energy, and the sigma star 2p molecular orbital is the highest energy. So if this is boron B2, and we filled out the molecular orbital diagram for boron. Well, boron has how many valence electrons? 3, right? So it's going to be these two, and then one of these, right? The sigma orbitals that come from the 2s orbitals, those are going to completely fill up. And then the 2 remaining electrons that come from the p orbitals, those are actually going to populate the pi 2p molecular orbitals, and they're going to do so that they're both half filled, because that is the correct. I think it's called the Aufbau principle. That is the right method on how to determine the electron configuration of something. You add a single electron to each orbital of equal energy until they are half filled, and then you start filling them. So in this case, we didn't even fill them because we only have two electrons coming in. So really, what we have for B2 is we have all of the electrons in a pi 2p. All of the electrons that come from the p orbitals are in a pi 2p molecular orbital and no other molecular orbital. We have 4 other empty molecular orbitals up here. We have the sigma 2p, the 2 pi star 2p molecular orbitals, and the sigma star 2p molecular orbitals. So there's B2. Let's try a different one. Let's try C2. So if each of the things on the outside is a carbon atom, then that looks like the 2s orbitals are going to be filled. And then we have, the carbon has 4 valence electrons, so it's going to look something like this. There's going to be 2 electrons in each of the whole p orbitals. So, okay, let's fill out the molecular orbitals. These are all going to be filled. And then it looks like we're going to fill up the pi 2p molecular orbitals entirely, because there's 4 electrons coming in. So this is what the molecular orbital diagram of C2 looks like. So this, obviously, this energy ordering is going to affect your calculation of bond order. I'm not really going to go over the bond order of all these homonuclear diatomic molecules. I'll just leave that to you to figure them out, or I'll touch on them in another video. So we did B2, we did C2. Now let's move on to N2. Okay, so this is N2. And these 2 are going to be filled up. The 2s electrons are going to be filled up. And then nitrogen has 5 valence electrons, so the remaining 3 valence electrons are going to populate the p orbitals in this fashion. Remember, you keep adding 1 until they're half full, and then you add them with parallel spins. So these are all going to be filled up once we do the molecular orbitals. The sigma 2s and the sigma 2s star, those are always filled up. And now we have 6 electrons coming in, so it looks like this is 1, 2, 3, 4, 5, 6. So now the sigma 2, or excuse me, the pi 2p and the sigma 2p molecular orbitals, these are all bonding molecular orbitals. These are all filled. So we would expect N2 to be very stable because it has a lot of electrons in bonding MOs, and it has almost no electrons in anti-bonding MOs. The only anti-bonding MO that is populated in the N2 molecule is the sigma star 2s. So a lot of bonding electrons compared to anti-bonding electrons. So that does it for B2, C2, and N2. Now let's talk about O2, F2, and Ne2. Now, like I said, the energy ordering of the pi and sigma molecular orbitals, the pi 2p and the sigma 2p molecular orbitals, is different for these 3 than it is for these 3. So in the case of, let's just say, O2, the energy ordering for the molecular orbitals that come from the p atomic orbitals are as follows. We have sigma 2p is the lowest, followed by pi 2p, followed by pi star 2p, and then sigma star 2p. So let me go back to nitrogen for a second, just so we can compare. In the N2 molecule, we have pi 2p, sigma 2p, pi star 2p, sigma star 2p. But then in the O2 molecule, we have sigma 2p, pi star 2p, and then sigma star 2p. So instead of the pi sigma, we have a sigma pi sigma. So this is the main difference between boron, carbon, and nitrogen, and oxygen, fluorine, and neon. So let's go ahead and do the molecular orbital diagram of O2. Oxygen has 6 valence electrons, so it's going to look like this. Okay. The sigma 2s and the sigma 2s star, those are going to be filled up. And then it looks like we have 2, 4, 5, 6, 8 electrons coming in from the p orbitals. So we can fill them in like this. So this is what the molecular orbital diagram for oxygen, diatomic oxygen, looks like. Now, in this molecule, we still have we do have an antibonding orbital that's populated by 2 electrons, or we have two antibonding molecular orbitals that are each populated by 1 electron. So we wouldn't expect O2 to be as stable as N2, for instance, because it has more of these antibonding electrons. But it's still pretty darn stable. Like I said, I'm not going to do the bond order, but you can probably figure out and deduce for yourself whether or not this is a stable molecule. So that's O2. Let's move on to F2. The energy ordering for F2 is going to be the same as it was for O2. So F2 has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. I'll do the same thing for the other fluorine atom. Okay. These 4 electrons are going to fill up. These 2 orbitals are going to fill up. And then we have 14 electrons coming in. Not 14 electrons coming in. We have 12 electrons coming in. 10 electrons coming in for the, I don't know what I'm thinking. 10 electrons coming from the p orbitals. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is what the molecular orbital diagram of the F2 molecule looks like. We have more and more electrons that are now populating these antibonding MOs. So F2 shouldn't be as stable as O2. And now finally let's move on to neon, Ne2. So neon has 8 valence electrons, so that means that all of these guys are going to be full. All of the p orbitals and all of the s orbitals in the valence shell of neon are full, which I think is one of the definitions of a noble gas, so that makes sense so far. When we start adding the electrons to form the molecular orbitals, as always, these are going to fill up, the sigma 2s and the sigma 2s star. And then it looks like we have 12 electrons coming in that come from the p orbitals. So 1, 2, 3, 4, should have populated them as 3, 4, 5, 6. And then 7, 8, 9, 10, 11, 12. So this is the MO diagram for the neon, diatomic neon. So notice that we have more and more antibonding molecular orbitals that are populated. So I think when it's all said and done, if we calculated the bond order for Ne2, then it would be 0, which makes sense because it has been known for a while that noble gases are not are very unreactive. So we wouldn't expect Ne2 to exist in nature. So I hope this was helpful, and in the next video I might discuss the reason for the energy ordering difference between these different types of elements. But for now, all you have to know basically is that, like I said, the energy ordering for these 3 is entirely different from the energy ordering of these 3. So